Welcome to our next lesson of vectors. Today we are looking at systems and intersection of planes. So our goal today is to be able to analyze systems involving planes and determine their intersection using algebraic methods. And really, you have already been doing this, so especially the solving systems of equations, but now we're going to see a bit of an algorithm, and this is actually a really helpful tool, and it has a lot of application in many different fields. So, for example, with coding, navigation, GPS, business models, anytime you have a long set of equations with many different variables, this system that or this algorithm that you're learning today is actually what is being applied in the background that's helping you or helping people in these fields, or even computer machines to solve a huge set of algebraic equations. But we're going to work with some smaller sets to see how it works. But again, it has a really large application outside of calculus and vectors. So to start us off, we are doing a bit of definition. So a linear system of equation is a system that can have 0, 1, or an infinite number of solutions. And again, we kind of already saw this when we were looking at intersections of lines and planes or a line with another line. And equivalent systems are two systems of equations that have the exact same solution. So any solution to one system will be a solution to the other system as well. And this is also it is a definition, but it can be also used as an if and only if. So if any solution to one system of equation is a solution to another system of equation, then we can conclude that these two systems are equivalent. So the algorithm we are going to learn is making use of the elementary operations, which are these three operations here. And so pretty much we are doing some algebraic manipulation to our system of equations in order to be able to solve it. So one thing we can do is, and one thing also with these elementary operations, you're not changing the system of equations as a whole. You are just making equivalent, and that's why we learn equivalent systems. You're creating equivalent systems such that as you change your different equations, the final set of or the final system of equations that you get, any answer you find there will be an answer or solution to the system that you originally started with. So one of the operations is to multiply an equation by a non-zero constant. So for example, if you have 3x is equal to 6, if I multiply this whole thing by 2, so I have 6x is equal to 12, then this still has the same answer. Here x would be 2, and here x would still be 2. So again, these two would be equivalent systems because their solutions will still be the same. You can also interchange any pair of equations. So let's say here I have 3x is equal to 6, and then I have 4y is equal to 16. If I change the order of these and write it as 4y is equal to 16 and 3x is equal to 6, the solutions to x and y that satisfy this system of equations, so this one is system 1, and this one is system 2, then all the solutions for this system are also solutions to this system. Changing the order doesn't actually change your solutions. And our last option is to add a non-zero multiple of one equation to the second equation. And this can sometimes replace the second equation as well. So, for example, in these two, I could also have, and I know right now doing this, you're going to be like, why would I do this? This doesn't really help me. But if I have 4y plus 3x is equal to 22, all I've done is add the 3x here, and these two are still going to be the same system as well. So as we do some examples, you'll see exactly why this one is going to help us. So, for example, we want to solve this following system of equations. So our first equation is 2x plus y is equal to -9, and the next equation is x plus 2y is equal to -6. So you already know how to solve this. You've been doing a lot of algebra. So really what you would do is find an expression for y using x and substitute that to be able to solve for x. And once you have your x value, you can substitute that back into your expression for y, and you will have your x and y values. But again, because we are thinking as a bigger picture to have many different equations and um, possibly have infinite many solutions for different systems of equations, it is helpful to get familiar with these elementary operations and how we use those. But again, as I'm doing this, I highly recommend you make connections to any general method you know on how to solve this system of two equations with two variables. So the first thing I do is I just do the elementary operation 2, which is interchange these two equations. And the reason I do that is I want this, I see this x has a coefficient of 1, and so I want this one to be at the top. So here now we have, again, this is just 2, and this is 1 now here. So I'm working with this as my preliminary system of equation. Now I multiply equation 1, so x plus 2y is equal to -6 by -2 and add it to equation 2. So this is now that third elementary operation. And the way we write that is the equation 1, which has 1 with a circle, is multiplied by -2 and added to equation 2, which again has that circle. So really, the -2 multiple of x plus 2y is equal to -6 is -2x, -4y is equal to 12. Now, I hope you can see that adding this to 2x plus y equals -9 will actually eliminate that x term there. So I end up with equation 3, which is 0 minus 3y is equal to 3. And as we move forward, you'll see that this is the way they write it, or the way it is written, you actually no longer include this. Because you are saying that you now have a new expression for equation 2, so you will just label this new equation as 3, and you go in order of your numbers. And so now you just have 1 and 3. And this is an equivalent system of equations as even this first one that we started with. So any solution to this will be a solution here as well. Now I perform elementary operation number 1, which is multiply my equation number 3 by -1/3. And the reason for that is I want to get the coefficient of y here to be equal to 1. And that way I have y is equal to -3, so there's my y value there. And now I use this y value and substitute it back into equation 1. And here I can solve for x. So doing so, x plus 2 times -1 will give me -6, so x is actually equal to -4. And as always, we want to do a check as well. So knowing that x is -4 and y is equal to -1. And now I'm actually using the very original system that I started with. So even the order of them is the same. So we start with 2x plus y equals -9 and x plus 2y is equal to -6. And I check whether my x and y values satisfy these two equations. And exactly, I see here that the first equation gives me -9 and the second equation gives me -6. So we did find a solution to the system of equations. Now, sometimes you'll also be given the x, y, and z values and just asked if this is a solution to the following system of equations. And this is pretty much what we're doing for the check. You're just substituting those values and seeing if they satisfy these two equations, which means here you should get 4, and in the second equation you should get 1. So substituting, we see that the first equation does in fact give us 4, but the second equation gives us 17, which is not equal to 1 as we were expecting here. So even though x, y, and z satisfy one of your equations, it isn't a solution to the system of equations because it doesn't satisfy both of them. So then we actually have to say, no, this is not a solution to the system because it doesn't satisfy both of the equations. So even when you're checking if there, for example, is an intersection, if you get an answer that satisfies one equation but not the other, then it is not a point of intersection because it would not be a point, for example, on each of your two planes because it'll only be a point on one of the planes. Now, again, we are talking just algebra. I will add in the plane portion after, but just with algebraic systems of equations, we also have now two definitions, consistent and inconsistent. Pretty much when your system of equations has a solution, which can be either one exact solution or an infinite number of solutions, then we say that the system is consistent, which means that you can actually solve for it. However, if there are no solutions, we say that the system is inconsistent. And again, as we work through some examples, you will see both cases of this, and we will make a connection between consistent and inconsistent when it comes to intersection of three planes. But before we do that, we're just going to get a bit of more extra practice with those elementary operations. So here we have a system of three equations and three variables, and we want to solve the system. So again, using algebra, you probably know how to solve this because it's three equations, three variables, but we are solving this with elementary operations. So here, I'm going to add in those extra steps for you here with the circles. And you do have to copy it down in your own work. You do have to show it as well. And I have actually given you the description of what I'm doing, but if you are just directly going to the next system of equation, so the next equivalent system of equation, you have to show your work. So we multiply equation 1 by -2 and add it to equation 2. So really, this is -2 times 1, and we circle it because it's one of the equations, and add this to equation 2. And you can see here now I have equation 4. So I don't write 2 anymore because these two, while they are equivalent, I am acknowledging that I have made some changes. Now, I also do, you can do two steps in one when you're changing two different equations. I also do that for equation 3, where I add the -3 multiple of 1 to equation 3 to get now equation 5. And as you can see here, now I have eliminated the coefficients of x in both variables, or sorry, in both equation 4 and 5. And so really, it's only equation 1 that has x. Now, we multiply equation 4 by a third because I want this coefficient of y here to be 1. And again, we do have to name this as a new equation. So this is 1/3 of equation 4, which gives me y minus z is equal to 3. Because here we had 3y minus 3z is equal to 9. So taking the third of every single term, left-hand side and right-hand side, you end up with this equation here. And now I have an x with a coefficient of 1, a y with a coefficient of 1, and now we have to tackle that last equation there by eliminating y there. So, and also pay attention here, we now have equation 6. Now we multiply equation 6 by -4 because this is 4 here. Over here we have 4y. So multiply equation 6 by -4 and add this to equation 5, which was 4y minus z is equal to 9. And now our new equation is 3z is equal to -3. Now here, you don't actually need to divide by 3 one more time and come up with equation 8. You can start solving it. And here it's clear to see that for z to satisfy this equation, z has to be equal to 1 or -1. And really what we do, we solve for z here and then substitute it back here because then we only have one variable y. And then you solve for y here. You have z and y, and now you can solve for x here. And this is called back substitution. And the idea is you're just finding the variables in a backwards order, but also you are starting from your last equation and then substituting back here and then substituting back here, and eventually you will solve for all of your different variables. So again, from equation 7, we have z is equal to -1, and substituting into equation 6, we get y is equal to 2, and finally, x would be equal to 4 here. And one last thing you would have to do here as well is your check. So knowing X, Y, and Z, you do go back here with your first system of equations, and you actually solve for each of these to see that you get 1, 11, and 12, and then you can conclude that this is a solution to this system of equations. For the sake of this lesson, I do have a lot of examples that I want to cover, so I'm not showing you the checks, but please do them in your own time and make sure you are getting equivalent answers for left-hand side, right-hand side. Now, another example would be, and this is more of a thinking question, you'll be given a system of equations with a random variable in there, which this variable is actually a scalar. And you're asked here, what value of k will give this system of equations to have an infinite number of solutions? So we have x plus ky is equal to 4, and kx plus 4y is equal to 8. So here, multiplying equation 1 by k and adding it to by negative k and adding it to equation 2. So really you're doing negative k by times 1 plus equation 2. Oh, and this should be now 3 because you have a new equation. Then we have negative k squared y plus 4y is equal to negative 4k plus 8. So really, if I factor this part out, I end up with k minus 2 times k plus 2 times y. And I just factored that y out, and then I have a difference of squares there. And on this side, I have, if I factor out the 4, k minus 2. And I also did multiply both sides by negative 1, so that's why those negatives are eliminated there. Now, in this equation, consider when k is equal to 2, then this will give us a 0 value. So really, you will end up with 0y is equal to, and this side will also give you 0, 0 here. So that means any value of y will satisfy this equation because k is 2. So again, in this 0y is equal to 0, any value of y will hold true. So technically, you have an infinite number of solutions here. And you can also show that when k is equal to negative 2, there are no solutions to this system because you will pretty much end up with your left-hand side and right-hand side not matching so that there will be no solutions. Now, I'm going to pause here to make a connection between this example and the last example. So if k is 2 here, I'm going to go back here. This will be x plus 2y is equal to 4. And here we have 2x plus 4y is equal to 8. And do you see that this is just the equation 2 is the equation 1 times 2. So generally when you have systems of equations, if you have n variables and you have anywhere less than n number of equations, then you will likely end up with an infinite number of solutions or possibly no solutions, such as this example here. These two are really the same equation, right? So that's why we end up with an infinite number of solutions. However, going back to this example, we had 3 equations and 3 variables, and so we were actually able to find one exact solution. And so, as a requirement, when you have n variables, you need at least n equations to be able to find one exact solution for it. And one more thing I want to point out here as well is this idea. So when you are using elementary operations, and again, think when you have n variables, the idea is you want to set up your equations in a way that you will have the first variable with a coefficient of 1 in your first line. Then all the other equations will have a coefficient of 0 for that same variable. So really, it's only equation 1 that is going to help us solve for x. Same with now y here. We only look at the coefficient of 1 in the second line for the second variable. So all the preceding equations will have a coefficient of 0 for y, and we're really using this equation to eliminate all of those variables of y. And we can continue on with however many variables we have in order to set our system up. So we have 0, 0 here, which is kind of like this triangle shape with the zeros, and then you will have all your variables with coefficient 1, and we could have done this for here as well. This would have just been z is equal to -1, and then back substitution will be applied in order to solve each and every one of those variables, because your last equation will just have one variable equal to a scalar. And again, solving for that last one, you can substitute back and solve for all the previous variables. Now, we did the algebra. Let's start making connections to our planes. So when two planes intersect, you can have that they intersect along a line, such as this example here. So if you have pi 1 and pi 2 as your two planes, these two are intersecting at this line. You can also have two parallel planes that will never intersect. And finally, you can have two planes that are coincident. So keep in mind, these two are also parallel, but more importantly, they are coincident. They are pretty much the same plane. And in each of these cases, how many points of intersection are there? So in the case 2, where you have two parallel planes, these two planes will not intersect at all. So you will actually have 0 points of intersection. However, a big difference that plays here when it comes to intersection of planes that's different from intersection of a line with a line and a line in a plane is that when two planes intersect, they intersect along a line, which means that any point on this line will be a point of intersection. So really, you actually have infinitely many points of intersection in this case. And same with here. When they are the same plane, any point on one plane is a point on the other plane. So you will also have an infinite number of points of intersection or solutions here as well. So, with two planes, when you have the system of equations, you will either have that they will have 0 solutions or an infinite number of solutions. Now, keep in mind what I was just telling you with n variables and n equations. In R3, when you have a plane, you have x, y, and z. You have 3 variables. But if you have two planes, so if you have pi 1, which is a1x plus b1y plus c1z plus d1 is equal to 0, and pi 2 is a2x plus b2y plus c2z plus d2 is equal to 0, then you have 2 equations and 3 variables. So you will not end up ever with having only one solution because we don't have that third equation in there. So you will either have infinitely many solutions, which is either when they intersect at a line or when they're coincident, or you will have that there are no points of intersection, so they are parallel planes. So consider these two planes here, pi 1 and pi 2. And we're asked to describe the intersection of these two planes. Now keep in mind, this can be any of those 3 cases that I just mentioned. So the first thing we check is if they are parallel. So in Cartesian equation, we have, or in Cartesian form, we have their normals. So here we have 1, -1, 1, but the normal for this one is also 1, -1, 1. And that's exactly here. N1 is equal to N2, and they are both equal to 1, -1, and 1. So they are parallel. So now we have either case 2 or case 3. So either these two are parallel and never intersect, or they are coincident planes. So if they are coincident planes, then we should have that any point on one plane will be a point on the other plane. However, if you look at their equations here, if you have an x, y, and z that satisfies x minus y plus z is equal to 4, then there is no way for that same x, y, and z to also produce 5. So then there is actually no solution to this system of equation. And using elementary operations, what we would have done is we have here -1 times equation 1 plus equation 2, and we get 0x plus 0y plus 0z is equal to 1. but there are no solutions there. So there is no solution to the system of equations. So these are parallel planes and they are non-coincident. So let's look at this next one now. We have x plus 5y minus 4z is equal to -1. And then our second equation, and these could be equations of planes, right, is 4x plus 20y minus 16z is equal to -4. Now, equation 2 can be written as, if I factor out the 4 from both sides, this is really just the equation 1, but multiplied by 4. So we can actually conclude that these two are coincident planes and have infinitely many solutions. Now, using our elementary operations here, if we do a quarter of equation 1, actually a negative quarter of equation 1 plus equation 2, then we end up with 0x plus 0y plus 0z is equal to 0. In this case, any value of x, y, and z that you choose, it doesn't matter because they all have a coefficient of 0, and so ultimately you do end up with 0 regardless of what x and y and z value you have. So there's an infinite number of possible values of x, y, and z that satisfy this equation, and so the planes are coincident. So now, giving you that as a theorem, if two planes pi1 and pi2 have normals n1 and n2 respectively, then we have these two cases. Either their normals are scalar multiples of one another, and in that case, they are either parallel and non-coincident or they're coincident. So if they are coincident, and again, keep in mind if they're coincident, it's pretty much the whole equation of one is a multiple, a scalar multiple of the other one, then we have an infinite number of solutions. And if they are parallel and non-coincident, then they have no point of intersection. And that's exactly what we saw with this example here. So you will see that no scalar multiple of one equation will give me the second equation and vice versa. Then the next case also is when those two normals are not scalar multiples of one another. And in that case, we definitely have that they intersect and they intersect in the line. So all we have to do is now find what that line of intersection is. And in that case, they also have an infinite number of points, given that these points are on the line that we find. So let's look at that case. Here we are given two planes, pi1 and pi2, and we're asked to find the nature of the intersection. And pretty much what that is you're saying if they are parallel, coincident, or they have a line of intersection. Now, the normal vector of plane 1 is 1, -1, and the normal vector of plane number 2 is 2, 2, -2. These are not scalar multiples, so based on this theorem here, we know that they intersect in a line. So we just have to find what that line is now. So if we multiply, oh, this should be equation 1, sorry. I was confused. Equation 1 by -2 and add it to equation 2. So this is -1, or sorry, -2 times 1 plus 2. You can see here that we end up with 4y minus 4z is equal to -3. Now, in this case, I can't do anything else because there's no other equation. So really, I have two variables in this equation, and I can't solve for either one. So what I really do is I express one as an expression of the other. But because we are looking for now a specific point, I have to give a specific value to one of the variables. So let z be s in this case. So then equation 3 is 4y minus 4s is equal to -3. And s is technically, we're saying it's a given now. It's not just any random variable z. Then y can be written as s minus 3 over 4. So now we have y and z as an expression of s. So now we actually have one variable for this whole equation. Now, I substitute this into equation 1, and I get from here, because this is, remember, z is s, and this is y in terms of s, then I get x is equal to 9 over 4. And the two s's do cancel each other out, so then x is just 9 over 4. Then we can actually write the parametric equation of the line of intersection. We have all of our variables x, y, and z as an expression of s, so we write it as such. X is equal to 9 over 4, y is equal to s minus 3 over 4, and z is just equal to s. Now, I can actually write this as a vector form as well, but you were just told to find the nature, so we just know that they intersected a line, and this is one form of the equation for that line. Now we also do check as well. So going back to our two equations for the two planes, so using the two Cartesian equations, I want to check that those x, y, and z parameters, or x, y, and z expressions in parametric form satisfy those two planes. So here, substituting for the equation in plane 1, I get 3, which is what we wanted. And same with plane 2, I get 3, which is what I wanted. So yes, that is the line of intersection for the two planes. So any point on this line will be a point of intersection of the two planes. Next, we have an example. We have to determine an equation of a line that passes through this point and is parallel to the line of intersection of these two planes. So we already are told that these two planes intersect at a line, but we want to know what that line is because we need its direction vector in order to determine this equation of this new line, which passes through this point as well. So the normal vectors for these two equations is, or these two planes is 1, 1, negative 1 for plane 1 and 2, negative 1, 1 for plane 2. These are not scalar multiples, so again, we were told this anyways, but we are double checking, so they intersect along a line. Now, remember cross product gives us the vector that will be parallel or perpendicular to both of these direction vectors. So, or sorry, these two normal vectors, and if it is perpendicular to the normals of these planes, then we can also conclude that it's going to be parallel to these actual planes as well. So finding the cross product here, we end up with 0, negative 3, negative 3. And really, this being parallel to the plane, being parallel to the line that intersects the two planes, then that's what we wanted, the direction vector there. So now this is the direction vector for that line we were trying to find. So now, knowing m is equal to 0, negative 3, negative 3, I just do some algebraic manipulation to find its scalar multiple, which is 0, 1, 1, which is simpler and easier to work with, more friendly. I also had the point that the line goes through, and this part is actually really easy. You're just writing the vector equation with the reference point, which was P, and now you have the direction vector there, which again was the line that, or sorry, the vector that is parallel to the line of intersection of these two planes. Now, if these two planes have their normals given to you by their Cartesian equation, then the cross product will be perpendicular to those normals as well, and so it will actually just end up being parallel to the plane, and that is our direction vector right there. Now, let's look at the intersection of three planes. So here we have two different cases. You will have consistent and inconsistent. So remember, consistent is when there is a solution, so you will either have one exact solution or infinitely many solutions. So one case is when the three planes intersect at a single point. So here you will actually have only one solution, and it will be point P. You can also have that the three planes intersect at one line, and in this case, you have infinitely many solutions across this line. And these are all three different planes. Another case you can have is when two of your planes are coincident and you have a third plane that's not coincident to these. And it is also, again, because it is a consistent, they do have to intersect somewhere. And so this is really just the same as intersection of two planes. You just treat you look at one of the planes and its intersection with the other plane and find their line of intersection. And your last case is if they are all three coincident planes. So any point on one plane is a point on the other two planes. And so again, you have infinitely many solutions in these three cases and only one solution in case one. So let's look at an example of those. So here, we're asked to determine the intersection of the following three planes. Now keep in mind, this can either be one point of intersection or a line of intersection, or they could be coincident. Now, right away, I see that these are not scalar multiples of one another, so they cannot be coincident planes. We also do check, and you can even do this like just visually looking at it. The normals of these planes will not be scalar multiples of one another. So we can also conclude that these are not parallel, and we don't have two coincident planes for any pair of the planes here. So our system of equation is now set up as such. We have 1, 2, 3 equations and 3 variables. So we expect there to be a solution. Now, and again, keep in mind, this is consistent, so there should be a solution. Here we use scalar multiples of equation 1 to remove the x term for both equation 2 and 3. So then I have 0 and 0 here. Now, we use equation 4 here because this is just y. And really what I do here is negative 4 times equation 4 plus equation 5. And then I end up with equation 6, which has that 0 there. So 0, 0, 0, and that's that triangle formation that we wanted. And now I also do have one variable here. Again, you don't have to divide by 12 and get equation 7 here. So you can just start solving right away. That would be okay. So using back substitution, we get z is equal to 2. Substituting back into equation 4, we get y is equal to 3. And substituting both of those values into equation 1, we get x is equal to negative 1. And so these three planes have a point of intersection at negative 1, 3, 2. You do have to do one extra step here as well. Again, I'm skipping it for the sake of time, but you will substitute these values back into your first equations here for each of the planes and see that you will get negative 2, negative 9, and negative 2 respectively. And so you can conclude that this point is on all three planes, and so it is a point of intersection for them. For this very last example, we have the following system of equations, and we're again asked to solve it. So we are using our elementary operations again. So here I am adding the scalar multiple of equation 1. So I'm multiplying by negative 1 to equation 2 to now get equation 4 to eliminate that coefficient of 0 or coefficient of x there. Now for equation 2, because here we have 3x, and I am just sticking with 3x here. The reason for that is if I divide by 3, I end up with a lot of fractions here. So as long as it's manageable, it's okay if you just keep 3x there. Our goal is just to make these two have a coefficient of 0. And now here, our goal is to get the y to have a coefficient of 0 using equation 4. So to get rid of that x coefficient first, I multiply a third of equation 1 and times negative 2 and add that to equation 3. And here we have that 0x. Now, to get rid of the y coefficient here, I do multiply. Oh, sorry, this should be removed here because it was from the previous one. So I just multiply negative third of equation 4 and add it to equation 5. And now from equation 6, I have 0x plus 0y plus 0z is equal to 0. And now, from equation 6, we can see that any x, y, and z value will give me a solution here. So we have an infinite number of solutions. So that means our system doesn't just intersect at one point, but rather we have a line of intersection. So I let z be equal to t, again, because we don't want to work with our x, y, and z variables because those are representing the coordinates. We more want to now create a solution set, and so we have to define some parameters here. So we let this z be equal to t, and from equation 4, now through back substitution, y is equal to 5 over 7t minus 3 over 7. And now I have two variables as an expression of just one variable, which is t. Now, substituting into equation 1, we get this following expression, and I have included here for you just to see. So 3x would be equal to negative 2y plus z, and this is just the values of y and z as an expression of t. So then you end up with negative 3 over 7, this should be t, plus 6 over 7, and then dividing by 3, I get negative 1 over 7t plus 2 over 7. So the system of equations has a solution given by x, y, and z, z here, with expressions for t. Keep in mind, their intersection is a line of intersection, and so we are trying to get that equation of a line. And I do have now one parameter here. So from here, it's really easy to set up your vector form of the equation of the line. So any term with t is going to contribute to your direction vector, and that's why we end up with negative 1 over 7, 5 over 7, and 1. Or with direction vectors, remember, you can use any scalar multiple, so I will multiply by 7 just to avoid having fractions there. And my new direction vector is negative 1, 5, and 7. Now, you can't do this with the point because the point is just a point. It's not a vector, so you can't just do the scalar multiple. So the line with the line of intersection will have the vector equation given by r, which is equal to, this is our point, and this comes from any term that didn't have t here. And because z is equal to t, it doesn't have any other term, so that's why z is 0. And then this is my direction vector times t for t in the set of real numbers. Because keep in mind here, when I let z be equal to t, I didn't specify what t is. T can be any real number here, and this will hold true. And again, remember we have infinitely many solutions on the line of intersection. And so that is our completed solution for this question. Now I am also, oh, and I did point this out to you when I did first start, but we do check always if they're collinear, especially when you're just asked to determine the nature of intersection of three planes, because one of the cases could be that they are all coincident, so they are scalar multiples of one another, or you have two coincident planes, or you have parallel planes, so you do have to check for that as well. But in this case, because they aren't collinear, we do have the case of 2a here, so they all intersect along the line, and we found the equation of that line. Now, I'm also going to show you the graphical representation of three planes that are inconsistent. So you can have, and this is where it is important to check that parallel part. So you can have a system of equations that's going to give you no solutions. So it will be inconsistent. One case of this is when a triangular prism is formed by three parallel lines, which means that if you are trying to solve the system, at one point you're going to end up with 0t is equal to 5, and you'll see that there's no value of t that would satisfy this equation, so you will actually end up with having no possible solutions for the system of equations. And this would be the graphical representation of it. So these three planes do not intersect. We do have the two of them intersect, each pair of planes intersects, but not all three of them intersect together. Another case is when two of the planes are parallel, so algebraically, that means they're in Cartesian form or in whichever form you have. You do have that they are multiples of the direction vector is multiples of one another. And in this case, you will have the third plane intersect each of those two planes. But again, no common intersection between all three planes. You can also have that all three planes are parallel. So in that case, their normal vectors will all be scalar multiples of one another. So in Cartesian form, you'll perhaps see all the A's are multiples of one another, same with the B's and the C's, but then your D terms are all going to be different. And that's what makes them parallel as compared to coincident. Coincident, remember, if you have AX plus BY plus CZ plus D is equal to 0, then any plane that is coincident will be a scalar multiple of this whole equation. Whereas with the case of the parallel, three parallel and non-coincident, these D values are going to be different. And finally, another case is when just two of the pairs are coincident and the last one is just parallel. So again, in all of these cases, you have no solution and no point of intersection between all three planes. And so I have explained to you algebraically how you can find these as well. So you do have some practice problems that will help you see those a little bit more algebraically. And over here, all I've done is all the different geometrical or graphs that we just saw, I've just given you a description of them. So here's the case with consistent systems when you have one or infinitely many solutions, and as well with inconsistent solutions. So these four all correspond to these four diagrams here, and these three, and this is also 2A and 2B, correspond to these three visuals here, or sorry, these four diagrams here. So again, please take some time to read that and make those connections. I have pretty much explained all of those individually throughout this lesson. And that was it for our lesson on intersection of planes. So you do have a lot of practice problems to help you practice all the examples that we did today. And as always, don't hesitate to reach out if you have any questions, and I will see you all next class.